Welcome to Lesson 12B, Compression Waves on Curved Walls. In this lesson, I'll introduce compression waves, which occur on curved walls and bodies with cusped leading edges. I'll discuss how compression waves merge into oblique shocks, and I'll show some photographs of merging oblique shocks and merging compression waves. First, a quick review. Here's an oblique shock going from 1 to 2, formed by a 2D wedge, or sudden change of wall angle, delta. When we ignore boundary layer thicknesses, the turning angle theta must be the same as delta, and beta is the shock angle. I'll call it beta 1 here for Mach number M1. Beta is the shock angle, theta is the turning angle, and delta is the half angle of this wall or wedge. And note that we're analyzing two-dimensional flows. A qualitatively similar flow happens when the flow is axisymmetric. Recall also the theta-beta-m relationship and plot, which apply to oblique shocks, where we plot turning angle theta as a function of shock angle beta for various Mach numbers. And recall we had the sonic line, actually a sonic curve, this green dashed line, where everything to the right has a subsonic Mach number 2 downstream of the shock, and supersonic Mach number 2 to the left of this curve. We also had this maximum theta line, or curve, where to the right of this red dashed line, the oblique shock is strong, and to the left it's weak. For a given Mach number, let's take Mach number 3, we start at the normal shock here, where beta is 90 degrees, and as you follow along, you reach the point of maximum theta, and then continuing down, we reach a minimum beta point, which represents the weakest possible oblique shock. The normal shock is the strongest oblique shock possible. Now consider flow along a curved wall rather than a sudden change. For example, a wall like this, with supersonic Mach number coming in, and total wedge angle or wall angle delta, as this eventually becomes straight. Or, similarly, imagine a cusped leading edge of a body in supersonic flow, which would look something like this, where it's aligned exactly with the flow, with 0 degrees here, and then again some curved wall like this. Again, we'll analyze only the two-dimensional forms of these. How are we going to analyze these? Well, let's start by taking small increments of this changing wall angle instead of being gradual. For example, let's take 3 increments of delta. So our wall is initially horizontal, and we have some theta 1, which will equal delta over 3 with a straight wall segment. The next theta 2 is also delta over 3, as is theta 3. So at each of these 3 points, the wall angle suddenly changes, but each of these are straight line segments. We'll get an oblique shock here from 1 to 2, where Mach number is M1 coming in horizontally, and I'll use Mach number 1 of 3 in my examples. Well, this first oblique shock has a shock angle beta 1, and the flow turns by angle theta 1, where this will be M2. At the intersection of these 2 segments, we get another oblique shock to region 3, and at this one we get a third one to region 4. As we go through this second oblique shock, the flow has turned again, and the turning angle is relative to the wall angle upstream of this shock. So this angle is also theta 2. And we continue to M4, which turns at angle 3 relative to this wall upstream, and the flow angle must match the local wall angle since we're neglecting boundary layer displacement effects. And I note here that we measure shock angle beta and turning angle theta from the local upstream flow direction, as I've shown here. Since these 3 turning angles, theta 1, theta 2, and theta 3, are all the same, we can think about this on the theta-beta-m plot, where I'll sketch a few Mach number curves. Let's let this one be our Mach number 3 for our example case, and let this be our theta 1, which is also theta 2 and theta 3. So we come across horizontally on this line, starting here at Mach number 3, and we go to a lower Mach number, perhaps Mach number 2 or 2.5 here, at the same theta, but notice that beta has increased. But in region 2, the Mach number is now m2, and beta 2, measured from the upstream wall, is this angle here, where beta 2 is greater than beta 1. So my other comment is that beta goes up as Mach number goes down, and angle beta 3 relative to this wall is the shock angle from 3 to 4, where if this is m3, then beta 3 is even larger than beta 2. So although my sketch is not very accurate, you can see that what happens is these oblique shocks angle in towards each other, and if I go up high enough here, they'll start to merge. In this case, we have only 3 increments, but this final total angle is delta. Now let's imagine 6 wall sections, or 20, or 100, where we have very small wall segments that are changing their angle very slowly, all the way to infinity, so we end up with a smooth curved wall. In other words, a smooth rounded corner. I'll sketch this case as a nice curved wall, which eventually goes to a constant delta. But where the curvature starts and ends, we have oblique shocks, actually an infinite number of them, and because each downstream one has a higher angle, they start to merge. This is a complicated region where things merge, and let me clean it up a little bit here. But eventually they all merge into one oblique shock of angle beta and turning angle theta, which is equal to delta. A streamline would go nice and smoothly through these so-called compression waves, and though I've only drawn 9 here, there's actually an infinite number, each one being a very weak oblique shock. In fact, each one of these compression waves is an infinitesimally weak oblique shock. And let me ask the students, what is the shock angle beta for one of these compression waves?
Well, since these oblique shocks are infinitesimally weak, wouldn't beta be the same as the Mach angle?
That's right, Jack. It turns out that beta is equal to mu, the local Mach angle, which is the weakest oblique shock possible, as we pointed out here on our theta beta m plot, namely beta min equal mu. And here it's the local Mach number, since Mach number decreases as we pass through all these compression waves. But recall that mu is the arcsine of 1 over Mach number. So mu, the Mach angle, goes up as Mach number itself goes down, since Mach number's in the denominator. So mu keeps increasing as we go through the compression wave. And because of that, each compression wave is steeper than the one upstream of itself, as I've drawn here. There's 2 reasons for this. Again, mu up as Mach number down, as we mentioned here, and the wall itself is curving steeper as we move along. In any case, these compression waves are going to eventually merge. I'll also comment that these compression waves are isentropic near the wall. They're isentropic because these Mach angles represent sound waves that are isentropic. But since there are an infinite number of them, they very quickly start to merge, and the flow is not isentropic away from the wall where these start to merge. Finally, suppose we're looking very closely at the details of this curved wall from what I like to say is an ant's perspective. What does the ant see? It sees all these compression waves merging into one oblique shock. If instead we have a giant looking at this same flow from much farther away, this area where the wall curves is tiny compared to the giant. So all this merging is going on in a very small region from his point of view. To the giant, this looks like a sharp corner, and all he sees is one oblique shock, where we're back to our original oblique shock analysis, going from M1 to M2, with turning angle theta the same as delta, and oblique shock angle beta. That's what the giant sees from very far away. So from the ant's point of view, from very close, all these compression waves must merge into one oblique shock of angle beta. I'll end this lesson with some photographs. This shows a two-step angled wall where we have the first turn and the second turn, similar to what I did with 3 turns at the beginning of this lesson. So these are oblique shocks that merge into one oblique shock. And here's a case of a curved wall, or a ramp, where there are compression waves in this region, which are very hard to see, where they eventually merge into one oblique shock. Real life gets complicated because of the boundary layers, both in this figure and in this one, where the boundary layers cause things to be a little bit different near the wall. But you can clearly see these oblique shocks merging, as we've been discussing. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.